Hi, all right, so more on sentential derivations today. If you're following along on the slideshow, which I recommend, this is slideshow 16 called Sentential Derivations, and we're in section 8 titled Conditional Derivation. So today, or in this video, what I want to do is just introduce a new style of derivation. So far we've been doing what we call direct derivation. And one key feature of direct derivation is that whatever you're trying to show in a direct derivation is at the bottom of your proof. So for instance, you've got some premises maybe, I won't write them down, and then maybe you've got a show line, and perhaps you're trying to show R, and you do some steps, and what's distinctive about direct derivations is that at the bottom of your proof, say line 10 maybe, is R, the thing you were trying to show here. What we're going to see is that when it comes to conditional derivation, that's not exactly how things go. And so to illustrate why we need another derivation technique, or another proof technique as we might say, we can think about the following kind of argument. So this argument says, premise 1, if P then Q. Premise 2, if Q then R. Therefore, if P then R. And if you think about it, that's a valid argument. That is, if you know that P entails Q, and you know that Q entails R, then if you know that P is true, you know that R is true. It's kind of like the transitive property for conditionals. So this is definitely a valid argument here. And so we need to be able to derive it. We need to be able to prove it using our system. But given what we've done so far, given the rules we've seen so far and direct derivation, we're going to have trouble doing this. And so let's think about why we're going to have trouble with the current rules that we have. Well, if you think about our arrow out rule, which would be the natural thing we'd want to use here, we'd want to sort of break these down in some way. Our arrow out rule says, to do anything with an arrow, you either have to have the antecedent or the negated consequent. That is, you either have to have P or not Q, or in this case, you either have to have Q or not R, and of course we don't have any of those. So we can't break those down in any kind of way. Furthermore, you'll notice if you look through our rules, we don't have an arrow in rule, so there's not really an obvious way to introduce a formula that's got an arrow like this. And the only kinds of rules that even apply to our premises here are rules that aren't really going to help us. For instance, we could do this. This is permitted by our rules. P arrow Q and P arrow, and Q arrow R. That's permitted. That follows from 1 and 2 by and in. But pretty clearly that's not going to help us get if P then R. That's not anywhere close to that formula there. So we're just kind of stuck with our current rules. There's no way we can prove that this argument is valid, even though we know that it's valid. And so that's why we have to have a new derivation technique which we're going to call conditional derivation. And let me just sort of illustrate the basic idea, or just sort of try to talk through the basic idea before we lay it out formally. So think about what we're trying to show when we're trying to show if P then R. We're trying to show that if P is true, then R is true. Here's another way to put that. We're trying to show, supposing P is true, we're not saying it is, we're saying supposing P is true, R is true. Here's another way of saying that same thing. On the assumption that P is true, assuming for the sake of argument that P is true, R would also be true. And it's that last way of thinking about this conclusion that's going to really sort of help us see how we go about doing this. To show if P then R is just to show that on the assumption that P, R is true. And that's what conditional derivation is going to do. It's going to say the following. It says if you want to show something in the form if P then R, you don't directly show this conditional itself. Instead, what you do is you assume that P is true, just for the sake of argument, and then you try to show that R is true. And if from the assumption that P, in this case, you can show that R, that's just what it is to show that if P is true, then R is true. So that's going to be the basic guiding idea behind conditional derivation. And let me show you how formally this works. So we're going to have a special rule in our system that says if your show line has as its main connective an arrow, an then you're entitled right underneath that show line, not several steps later, but right on the next line, you're entitled to assume the antecedent is true. That is, you're entitled to assume, in this case, P. So we write down P, and the notation is AS for assumption. And you're allowed to do this because your show line has as its main connective a conditional. Immediately after you make that assumption, if you're going to go this route, you have to then write down another show line where the show line is the consequent of the conditional, in this case, R. And so what we've done here is we've said, okay, we're going to assume that P is true and see if we can derive R. See if we can show R from the assumption that P. And if we're successful in showing R, that will just be enough to show that if P is true, R is true. Because after all, what we're doing is saying if P is true here, assuming P is true, R is true. So that's how we set up a conditional derivation. And let me just show you how this proof then, or this derivation, finishes. Now that we've made this assumption, we've got 3 lines available. In addition to 1 and 2, we've also got line 4, our assumption here. And that makes all the difference, because now we can actually start to break down these premises. So from 4 and 1, I hope you can see we can get Q from arrow out. So we're going to write down Q from 1 and 4 by arrow out. Now we've got Q, and we've got Q arrow R, so we can get R again by arrow out. That's from 2 and 6 by arrow out. And look, we were able to do it. From the assumption that P, we were able to derive R. And so now we just need to finish up our proof, and let's just be careful in explaining each step here. So we set out to show R. That was our last, most recent goal. And R is at the bottom of our proof. So our derivation of R in this case is a direct derivation, because we wanted to show R, and there R is. We directly derived it. So we still write DD here for direct derivation. And then we cancel, and we box everything underneath that show line. And we're almost to the point where we're going to explain why we do that, but not quite. Now let's see what happens here. From the assumption that P, we were able to derive R. That's what the canceled show line means. That the slash through means, yeah, you've shown that. That's been established. So from the assumption that P, we established R. That is, assuming P, R is true. That is, if P is true, R is true. Just what this says. So we're allowed to now cancel this line. But here you'll notice P arrow R is not at the bottom of our proof. We didn't directly derive P arrow R. Instead, we will say conditionally derived it. That is, on the assumption that P, we showed R. And so we write CD. We cancel our show line, and then again we box everything underneath that show line, including the box we already had and the show line we already had, like this. And that's what conditional derivation looks like. It only applies in these special cases where your show line has as its main connective a conditional. You can't apply it in any other case. But when your show line has as its main connective an arrow, it's a really, really useful way, and sometimes the only way, to proceed and finish your derivation. So in the next couple of videos, I'm going to go through some practice problems, the practice problems, in fact, that are on the slideshow on page 44, I believe. But this introduces the concept, and now you can, once you sort of feel like you got the concept, you can go look at those practice problems and those videos to see some extra information about how these derivations work.